Good morning, everyone. My name is Shubhankar Potnis from the Department of Electronics and Telecommunications Engineering, Vidyalankar Institute of Technology, Mumbai. Today, I will be presenting my mixed signal VLSI mini project titled A Comparative Analysis of Two-Stage and Telescopic Cascode OpAmp Topologies for High-Speed Comparator Applications in 180 nanometer CMOS technology. This work was carried out under the guidance of Professor Akhil Masurkar. In modern electronic systems, especially in communication, imaging, and digital instrumentation, high speed analog to digital converters play a very important role. Among all ADC architectures, the flash ADC is the fastest because it completes the entire conversion in just one clock cycle. But this speed is limited by one key block, the comparator. In many designs, instead of using dynamic comparators, high gain operational amplifiers in open loop mode are used as comparators. But the performance of these amplifiers depends heavily on the topology used. In this project, I designed, simulated, and compared two popular OpAmp topologies, the two-stage OpAmp and the telescopic cascode OpAmp, to check which is more suitable for high-speed comparator applications in 180 nanometer CMOS technology. The main objective of this project was to design, simulate, and compare two different operational amplifier topologies in Cadence Virtuoso in 180 nanometer CMOS, especially to evaluate their performance as comparators. The comparison is based on the following parameters: open loop gain, propagation delay, slew rate, and power consumption. I used Cadence Virtuoso as the simulation platform. The technology used was 180 nanometer CMOS and the supply voltage was 1.8 volts. I performed three main type of analysis. First is AC analysis, which I use to calculate open loop gain and observe frequency response. Second is transient analysis, which I use to measure propagation delay and slew rate, which are very important for comparator operations. And third is power analysis to calculate static power consumption. This is the two-stage OpAmp topology. It has two main stages, a differential stage and a current mirror load. Wait, a differential input stage with a current mirror load and a common source output stage. It is simple to design and provides a large output swing and reasonable gain. However, to make it stable in closed loop mode, it needs Miller compensation, which adds an internal capacitor. This compensation capacitor slows down the circuit when it is used as comparator because it limits the slew rate and increases the delay. The second topology is the telescopic cascode OpAmp. This is a single stage fully differential amplifier which uses cascode transistors to increase gain. Compared to the two-stage design, it gives higher open loop gain, much higher speed, but it also has some disadvantages, such as reduced output swing, more complex biasing, and needs a common mode feedback to stabilize output DC voltage. So this is the common mode feedback circuit. For both amplifiers, I used the following simulation setup. AC analysis, I used the common mode input as 1 volt. For differential input, I used a plus and minus 0.5 volts. For transient analysis, the reference voltage was 0.9 volt. The input pulse was 0.8 to 1 volt to 0.8 volt, back to 0.8. Then I calculated propagation delay, that is the time difference between input crossing 50% of voltage reference and output reaching 50%, and slew rate, which is uh, which is the maximum slope of the output voltage. These values help us understand how good the amplifier is as a comparator. From the AC analysis, I observed the following results. The two-stage OpAmp achieved an open loop gain of 44.7 decibels, and the telescopic cascode OpAmp achieved 48.1 decibel. This higher gain in the telescopic OpAmp design is because of cascode transistors, which increases the output resistance and hence the overall gain. And here we can also observe that as the gain increases, uh, even if the telescopic op-amp has a higher gain, it also has a higher bandwidth. It covers uh, a higher range of frequency, while the two-stage op-amp gives a less gain as well as it has a less bandwidth. From the transient analysis results, the propagation delay of the two-stage op-amp was 12.5 nanoseconds, while the telescopic op-amp had a delay of only 4.8 nanoseconds. Similarly, the slew rate increased from 55 volt per microsecond to uh, in the two stage to 170 volts per microsecond in the telescopic amplifier. So the telescopic design is approximately 2.6 times faster, making it more suitable for high-speed comparator applications. However, this improvement in speed comes with a cost. The two-stage op-amp consumed 4.2 milliwatts, while the telescopic cascode op-amp consumed 6.8 milliwatts. This increase in power happens uh, because telescopic design uses more bias current and the common mode feedback circuit. So here is a clear trade-off. Higher the speed and gain, higher is the power consumption. So to conclude my entire work, the telescopic cascode op-amp provides a higher gain and 2.6 times faster response, making it suitable for high-speed ADC comparators. The two-stage op-amp is simpler, consumes less power, and has larger output swing, making it suitable for low power and general purpose applications. So the choice between the two topologies depends on the application requirement. If speed is critical, use telescopic op-amp. If power and simplicity matters more, then use two-stage op-amp. So thank you. Thank you for listening to my presentation. I would be happy to answer any questions.